Okay, we got 2 more minutes. If you already finished, you can pass to me. Great. Make sure you put your name there. Let's see, Nick, everybody. Try. Great, David. Mm-hmm. Mm-hmm. Okay, let me start. Okay. I got it. Thank you. Did I get everyone's? I think that's great. We actually finished 1 minute before the deadline. So let's begin today's lecture. Again, everybody know me well by now. Dr. Gu. I'm happy to share another lecture about polymer thermodynamics, polymer solutions. What are going to be the exciting things about today's lecture is we're going to dig deeper into polymer lattice theory. We're going to talk about, like I said in the quiz, what is entropy and enthalpy's role in polymer solution property. And we're going to go deeper. What I mean by deeper is we're going to examine exactly the reason how much enthalpy has contributed and how much entropy has contributed in the solution mixture. We're going to start with a very simple case. Binary mixture of solvents mixture, so that each solvent is perfectly independent. There's no covalent bond link me to my neighbors that if he moves, I need to be tethered and go around with it. It impacts, as you can imagine, the entropy of the system a lot. So we're going to go back to that part immediately following the lattice theory we're talking about today. So for everything we're going to talk about now, we only concerns about very simple case, mixing of solvents, mixing of toluene and hexane, for example. So a couple high-level understanding how they would mix or not is we need to understand a little bit model of the mixture. How are the molecules being able to arrange themselves? What type of interaction are present? This is more relevant to the entropy, and this is more relevant to enthalpy. Apply the statistic thermodynamics is what we're going to do, some of them today. Look at what is the delta G mixture and understand how does the delta G be influenced by these two entropy and enthalpy effects. So regular solution theory. And this is a very basic theory as given by this title. And what is this? How does this will be relevant? This is a very simple theory that which approximates the molecular origin of the macroscopic thermodynamic behavior. Sounds very odd and mouthful, but it basically says we can use simple thermodynamics to model if your solvent's molecule will mix or not. It is very simple, and we will see why, because it won't take 1 or 2 lectures to cover those from the ground up. From no physics background, not requires a little bit math background, but not a lot. You can actually cover the theoretical treatment of the mixture of the solutions. There's a couple assumptions, so we need to cover them before we talk about it. It's not a perfect model. We're going to be candid and be honest about what the simplification we did to our system. In the entropy, we're just going to be simply a computer from a number of possible arrangement of molecular. Right? We talked about that a little bit in last lecture. We talked about what is omega and how does number of possible arrangement affect the entropy. We're also going to talk about enthalpy. What this means is it's going to understand the change of interaction energy between the molecular surface during the process of mixing. Okay? So a little bit more entropy. In the rule of the statistical thermodynamics, it is permissive to break the entropy of the system into several components. We're just going to break down into each component, then add them together. There's a couple more details. We're not going to cover too much, all these different degree of freedoms in the translational or molecular rotation and vibrational. We're only going to consider how they arrange with respect to each other. The other part is the entropy's contribution to type 1 to 3 do not change upon the mixing. So it doesn't contribute to delta G. Make our system much easier. So we're only going to consider this part. This is the configurational entropy, which means how much different potential states you can adopt. And I'll go into more detail what I mean by that. So in the lattice theory, let's first talk about enthalpy change. So a very simple way to understand enthalpy is how does your polymer packed into a lattice. And that's where the name lattice is come from. So lattice model, basically, you can approximate any molecule to fill a specific volume with continuous space on the lattice side. So for example, here we showed a couple of different lattice spacing. So in the square, this is a planar. So this case, a lattice basically says a molecule has to fill in the black dots, and it has different neighbors around it, as shown. This has 4 closest neighbor. It will make an impact in the later part. Here you have a lattice has 6 neighbors to say neighbor if it's hexagonally lattice, etc., etc. You can think about different lattice. We can start with a very simple one to think about a square lattice. That's what we show in the other day. We draw a box with square lattice in it. Then we can use that lattice, how to pack molecules in it. One assumption is that all the small molecules will be represented by spheres of equal volume, so that we can throw in the lattice without worrying about their volume effect. Let's say hexane toluene, we're going to put it in the lattice and assume they're going to be equal. One very good and relatively okay assumption. The size of lattice cell will be equal to molecular volume, so all the size of lattice will be occupied. And the last one is relatively important. Each molecule has number of the closest neighbors. Okay, Z represents how much closest neighbor you have. And we only consider short-range interaction, so this matters a lot because if I look at in this classroom, we are roughly a square packed lattice because everyone is on a grid pattern. So if you look around, the whole classroom has maybe 16 students. Some of them are not here today, but you look at your closest neighbor, you should have about 4. That's what a square lattice. Your number 5, 6, 7, 8 neighbor closest is going to be a little bit away because you're going in diagonal, right? If you're looking at your closest neighbor, it should be your left, right, front, and back. This matters when we consider the enthalpy because we just need to consider the pair of the interaction. how much different interaction we potentially have, we also want to store this simple interaction in terms of enthalpy. So let's assume your system has basically two molecules represented by black or white, or in this case red and white. So as I imagine the interaction of hexane, let's assume the white one is hexane, the red one is toluene. The toluene and toluene molecular interaction will be quite different with hexane. So that's what determines the enthalpy. Before you're mixing, you have a beaker of toluene, you have a beaker of hexane. And there's only homo interactions between itself. Hexane interact with another hexane molecule. No matter what that hexane molecule is swinging around that giant beaker, it's only confined itself. Not exactly itself, but a copy of another hexane. But you get the point. The toluene the same. However, when you mix them, now you have a more complex system. You have a larger beaker, you fill in toluene hexane. What is kind of new interactions happening there? We only consider interaction force between two. What's new? You have, Jeff, I know what you want to say. You must want to confirm. We have now new interaction between toluene and hexane. Perfect. Do we still have a toluene-toluene interaction? Possible, right? If you mix equal volume of toluene hexane together, the chances of finding another hexane versus another toluene is equal. It's assuming that equal volume. You have 50% of meet one toluene and one hexane. That's slightly complex, our problem, but not a lot. We're going to talk about the next slide.
9 factorial.
Yes, that's right. We will explain why that's the case today. That's the answer, which is the show here. Number of possible state omega equals to total number of molecular in this system. This is a little bit slider. We only have 6 boxes. We have 8 white, 8 red. And we want to consider what's a possible arrangement out there. The answer is total number of possible state equals to total number of sites. N represents total number of sites. In this scientific case, N would be equals to 16 because we have 4x4 grid. And I'll explain why that's the case. And divided by factorial of white box and factorial of red box. Okay? So why? It's very easy to consider we are filling a box because we are doing different ways to fill the box. So we can fill random box from the top to bottom or bottom to right. It doesn't make a difference. For any given letters, for the first one, we want to fill a molecular. We got a total of 16 molecular. So the first one we will be able to fill you have a choice of either number 1 to number 16. Once you fill this one, this is the filler. We can cross it away. Pick another one. You has now 15 balls left, and how many different ways you can arrange them will be determined by 1 out of 15. So the total possible ways of a sphere into each lattice sides is given by total number of lattice sides m factorial. So in this case, it's going to be 16 multiplied by 15 multiplied by 14 all the way down. So it's a fairly big number you can fill in this particular box of 16. Okay, so but there are some duplicates in the way we fill. As we mentioned, hexane and hexane 1 and hexane 2 and hexane 8 are identical. So no difference. So let's assume you randomly fill the bar, but all the red color is the same, but only the order of filling is different. So you put this one first, then there, then or the other versus you this way. But because red is identical, so no difference between these two. So we need to take away those duplicates. Okay, remove all these duplicates in our system. And how many total duplicates in the system is given by duplicates when we consider all the white and duplicates when we consider all the red. And duplicates for the white is, we only need to consider how many ladders of the white. There's a total of 8, so it's going to be 8 factorial. It doesn't matter. I feel it this way, 1, 2, 3, 4, 5, 6, 7, or I feel 1, 8, etc. So it's indistinguishable between these two. And we need to take away the white, the other color ball as well. So it's always going to be defined by possible states. Lawing, this is very complicated, especially lawing of factorial. We need to adopt a little bit simple math to solve this problem. So if you look at appendix, there's a Stirling's approximation. Lawing n factorial will be equals to n multiplied by log n minus n. So this help our life much easier. So let's apply this particular equation into our entropy possible state setup. Once we apply, we can break down this long equation into log m factorial minus log m1 factorial and minus log n2. And we apply this Stirling's equation to each of them. The first part will be expanded to this portion of the equation, and log m minus m. The second part will expand the same for this part, but there's a minus sign, so remember, this is going to be minor, and minor m1 will be now converted to plus m1. Same here. One simplicity, as we know, we can start to sort away some of the unnecessary portion of the equation, especially m as total number of the molecular will be equals to m1 plus n2. So we can cancel out these two as I mark as red and only left this portion. And we can do some additional simplification for that. Where, as we show, again, this can be simplified into log x1. Where the x1 comes in? x1 defined as the volume fraction, a mole fraction of how many m1 molecular is. Okay, where is x1? x1 will equal to how many moleculars and moles in the molecular one or red molecule divided by total number. So if I mix 1 mole of red versus 1 mole of white, x1 will be equal to 1 divided by 1 plus 1. So 50% is what you have. If I mix 25%, 1 red ball and 3 white, the x1 will be 1 divided by 1 plus 3, 25%. Okay, that's what x1 is. Any question for this particular part? And how we get this from here to here is fairly straightforward. We break down this long equation into two parts, n1 multiplied by log m1 plus n2, and minus m1 log m1. So this, let me get a pen so that I can help everybody understand a bit. There might be a little bit confusion there because we jumped one quick step. That's the first part. Minus n1 log m1 and minus, I don't have space, so I'm going to write in the bottom. So we're going to take this common piece n1. So we took this part, and this part is given by here. we're going to minus n1 log m1. Okay? What left is a symmetric part. Now you have what left is n2 multiplied by log n1 plus log m2 minus n2. Almost symmetric equation. One of the beauty of the log is they have a shear of both m1, so you can take them out. And log n1 plus n2 minus log n2. So this is something you need to know to get this equation right. This is going to be equals to log x divided by y. Okay? If you know this, you can basically convert the top part to b. Right? And you would have another n2, the same. And this basically is what we define x1 minus 1. So you would left as m1 log x1 minus 1 plus this is x2 minus 1. And if you put this exponent term to here, this is another log x power of y will equal to y multiplied by log x. Okay? You would be able to reach this same relationship as written here. So that's the entropy after we mix them. What about the system's entropy change before I hold in two beakers? Before I dump them together? This we call status 1 before, and once we mix them, we shake it, we call status 2 after. So delta mix will be after my quite a beautiful equation. It's so symmetric, right? And or it can be written as a gas constant. R equals to basically Avogadro constant multiplied by K. So these two are the same, except that we now can use moles instead of number of molecular. 1 mole equals to, I think that's 6 multiplied 10 to the power of 24 molecular, okay? So that's the difference, 1 mole versus 1 molecular. And gas constant R is a value equals to Avogadro constant multiplied by K. So these two are basically, you either putting Avogadro constant here or combining there using say. Okay? Which is basically say that Avogadro constant and multiplied by K, Boltzmann constant equals to gas constant. So that's the same as that, but the only difference is we can count per lattice sites or per moles of sites. No, not much difference. Okay? Since the mole number fraction or number fraction, so how much A is in the B, when you mix them, A with B, you cannot mix it such that A is larger than 100%. It doesn't make sense. When you mix some red into green, a red molecule into white, it's always going to be 0% or 100%. It's not going to be over 100%, right? So the mole fraction will always be less than 1. This equation tells you this log x, this value will be a negative value, okay? Log x will be negative value, as shown here. If x is less than 1, your y, log x will be negative 0.5 or negative 1 or whatever negative value it is. X will be a positive value. So this term will be a negative. And there's negative sign in front of it. So combined together, delta x mix will be always an increase in configurational entropy upon mixing. It goes around. It basically says when you mix two, entropy goes up. Makes total sense. Okay? So this gives you simple approach to calculate how much entropy increase. But this effect of molecular interaction of entropy are overshadowed by KT. What that means, the molecular interactions will be also need to be considered. We only consider entropy. How about enthalpy? When you mix them, is there any heat change? Any differences? So in the next few slides, we're going to explain the enthalpy change in the lattice theory. When we mix two, how enthalpy changes. As I mentioned, entropy always promotes mixing, but enthalpy may not. It might be like it may not like it mixing. So let's figure out why. First, we need to find cohesive energy density is basically by how much energy you need to vaporize given liquids. Why this is useful? Because in liquids, we can approximate to be, there's no long-range order, but these liquids. In the regular solution theory, we basically assume a couple things. I'll spell the assumptions, what are these, to help us better explain the enthalpy changes. So these are no volume change upon mixing. When you mix toluene hexane, you put in 1 liter to another liter, it will be exact 2 liter, which is close but not exactly right. As we know, sometimes they do have volume reduction when you mix two solvents together, but it's not that big that will overthrow our conclusion here. So the second one is material is incompressible, so the size of laser site do not change, therefore pressure has no effect. Why? Because silicon thermodynamics term also has a pressure term. Pressure versus volume have a certain influence on your final performance. But we certainly don't want to see their influence here. So we say pressure, we temporarily don't consider its impact. Last one, the surface of molecule is homogeneous. It does not matter where on the surface of the contact all points are equal. This basically allows you to generalize interaction term for a two molecular within the liquids. Okay, let's define a few things. First, what is W11? This W11 is interaction parameter between interaction energy. So this is the energy associated between two pairwise interaction between two molecular. So if I put in red molecular, there is certain interaction. As I mentioned in last slide, there could have Lennard-Jones interaction, dipole moment interaction. But let's generalize. I'm probably going to have an astronomical number of molecular. How do I count total energy within the beaker, which is defined by this equation? Let me walk you through what that means. W11, as we know, it's just a single action between two molecular. Z defines number of closest neighbor. And this is related to the assumption that the pairwise interaction is not just a 1-to-1. So let's say, Jeff, I might use your example again. You're going to have, sitting in the classroom on the grid, you have 4 closest student neighbor. So each of them will share and enforce N11 force on you. So you're going to have 4 times N11 force. That's total number of energy interaction. But you with the other student, like Christian, it's going to be too far away. So we neglect this long distance force. We only count the closest neighbor. And Z basically tell you how many closest neighbor is. This can be a number like 4 or 10. Depends on how your molecular is packed, okay? M1 is number of molecular in the system. So you count how many neighbors, how many molecules you have, multiplied by how many interaction between you and neighbors. That's things make sense. But what is this 2 does here?
The interaction is between two molecules.
Yeah. So there's some duplication. So I count my interaction, for example, with Penelope, but when I count in the Penelope interaction means me, it's the same, but we duplicate. So that's why this m need to be divided by 2, okay? That's the reason. We always have a 2 because the interaction requires 2 contact points. Same for W11 is all the toluene interaction. W22 is the hexane interaction. So before we mix, that's how enthalpy for my left-hand beaker is the enthalpy for my right-hand beaker. Okay, make sense? Okay, so this is going to be a little bit tricky. Don't be scared by my writing there. So this is basically now asking you to imagine I dumped toluene hexane again to a giant beaker. We counted the enthalpy. Now, how about we counted the entropy in just a few minutes. How about enthalpy? How do we count then this complex beaker when I have toluene interaction, when I have toluene hexane interaction, when I have hexane interaction? How do we visualize and count in the new energy state for the mixed state for its enthalpy? Where should we start? Where should we start? We need to count number of contacts. How many contacts are between the contact point? There's also the second half I haven't finished. Again, you need to count male student interacting with female. So number of male students divided by 2. 2 is just the chance of interacting. Considering the pair interaction, we need to divide by that. You would also have the other half the chance. X2 is basically equals to number of molecular 2 divided by total number. X1 plus X2 will always be 1. Okay? So you have 50-50% mixture. That means X1 will be 0.5, 0.5. So now we already counted the homo interaction. What about heterogeneous interaction? For each male student, it needed to interact with a female student. Number of close neighbor, chances of meeting a female student, and interaction strengths with a female student, which defined by W12. We need to count the other way as well. Female student divided by 2. Chance of meeting a male student, closest neighbor of packing, W12 interaction. And consider the last part is 2-2 interaction, which I wrote here as red balls, etc. But they make the same point. At the end of the day, my hand is a little bit clumsy. So, what we should do now? We consider the W12 together and know the W22 together. It will give you this delta H mix. Sometimes code doesn't display correctly here, but it should spell MIX given by this equation. Or you can simplify as given by here, N1, number of red or toluene, okay? How many of them? M2. The other solvent you're trying to mix. So delta H mixing is unclear. The term and the concepts in the solution mixing. And in the next class when we return, we're going to apply everything we learned and show you an example. I talked to hexane toluene many times. If I give you a chi, we can calculate what is delta G value for that. And we will show a few examples how to apply this lattice theory to understand solution mixture. Okay?